Today, we're diving deep into one of the most fundamental topics in thermodynamics, the steady flow energy equation, or SFE. This equation is crucial for understanding how energy is conserved and transformed in systems where fluids are continuously moving. If you've ever wondered how energy behaves in dynamic systems like turbines, compressors, pumps, or nozzles, this video is for you. We'll explore the principles that govern these essential engineering components. Before delving into the equation itself, let's first understand the concept of steady flow. In a steady flow system, the mass and energy entering a control volume per unit time exactly equal those leaving it. This implies a constant state within the system over time. This means that conditions such as pressure, temperature, and velocity at any given point within the system do not change with time. Imagine a continuous process where the fluid properties at a specific location remain constant, even as the fluid itself flows through. To formulate an energy balance, we must identify all forms of energy associated with the fluid. These include internal energy, which is the energy stored within the molecules, kinetic energy, due to the fluid's velocity, potential energy, related to its elevation, and flow work, which is the energy required to move the fluid across the system boundary. Flow work specifically represents the energy needed to push a unit mass of fluid into or out of the control volume against the prevailing pressure forces. It's a critical component when considering energy transfer in flowing systems. For a unit mass of fluid, the total energy entering or leaving the system is expressed as H plus V squared over 2 plus Gz. Here, H represents specific enthalpy, which is a combined property of internal energy and flow work. V is velocity, G is gravitational acceleration, and Z is elevation. Applying the first law of thermodynamics to a steady flow system, we state that the rate of energy entering the system must equal the rate of energy leaving it. This is because, in a steady state, there is no accumulation or depletion of energy stored within the system. This energy balance includes not only the heat and work interactions between the system and its surroundings, but also the various forms of energy carried by the fluid itself as it flows through the system. The full steady flow energy equation is expressed as Q dot plus M dot equals W dot plus M dot. This comprehensive equation accounts for all energy transfers and transformations in a steady flow process. In this equation, Q dot signifies the rate of heat transfer to the system, W dot denotes the rate of work done by the system, and M dot represents the mass flow rate of the fluid. Each term plays a vital role in the overall energy balance. Rearranging the terms, we arrive at the SFE in its most practical and commonly used form, equals plus over 2 plus G. This form highlights the changes in energy per unit mass. This rearranged equation effectively relates the net heat and work interactions per unit mass to the changes in specific enthalpy, kinetic energy, and potential energy between the inlet and outlet of the system. It acts as an energy accounting system for flowing fluids. The true beauty of the SFE lies in its versatile application to a wide range of real-world engineering systems, such as a steam turbine, where it helps analyze performance and efficiency. In the case of a turbine, heat loss to the surroundings and changes in potential energy are often considered negligible. This simplification reduces the SFE to W dot over M dot equals H1, H2, making calculations more straightforward. This simplified equation clearly indicates that the work done by the turbine per unit mass of fluid is directly proportional to the drop in the specific enthalpy of the steam as it passes through the turbine. This principle is fundamental to turbine design and operation. For a nozzle, there is typically no work interaction, and heat transfer is often considered negligible. Therefore, the SFE simplifies to H1 plus V1 squared over 2 equals H2 plus V2 squared over 2, focusing on the interconversion of enthalpy and kinetic energy. In a nozzle, as the fluid flows through, its enthalpy decreases while its velocity significantly increases. This process effectively converts the thermal energy stored within the fluid into kinetic energy, accelerating the flow. To apply the SFE correctly and accurately, it's crucial to remember several key assumptions. The system must be operating in a steady state, meaning properties don't change with time. There should be a single inlet and outlet. and the flow at both the inlet and outlet should be uniform across the cross-section. The SFE is particularly well suited for analyzing steady, continuous flow systems. These include common engineering devices such as turbines, compressors, nozzles, heat exchangers, and pumps, which are integral to many industrial processes. In summary, the steady flow energy equation is a fundamental and indispensable thermodynamic tool. It provides a powerful framework for connecting heat, work, and various energy changes within systems involving flowing fluids. This equation forms the bedrock of design and analysis for critical technologies like power plant systems, jet engines, and refrigeration cycles. Understanding SFE is essential for comprehending how energy is managed and utilized in the machines that power our modern world. If you found this video helpful and gained a clearer understanding of the steady flow energy equation, please take a moment to like, share, and subscribe for more easy to understand engineering videos. Your support helps us create more valuable content.